Not anytime soon. Hawking radiation is incredibly faint, many times weaker than the cosmic microwave background. To build a detector sensitive enough, we would need breakthroughs in quantum coherence, error correction, and noise reduction. Technology's still in their infancy, and even if we could build one, it would take billions of years to collect enough radiation from an evaporating stellar black hole. Still, physicists are not discouraged. The quantum information approach to gravity is now one of the leading research areas. Scientists are exploring whether spacetime itself is built from entangled bits of information, so called it from qubit. In that case, understanding how black holes store and release information may one day help us unify quantum mechanics and general relativity. So, to return to the central question, could future detectors recover lost quantum information from a black hole? Theoretically, yes, if information is truly encoded in Hawking radiation and if we can build unimaginably sensitive quantum instruments. But practically, this remains one of the most distant frontiers in physics. It is less about building a machine today and more about reshaping our understanding of what space, time, and information really are. The black hole information re-entry problem is one of the most fascinating and unresolved puzzles in modern theoretical physics. It touches on the nature of quantum information, the fabric of space-time, and whether what falls into a black hole is truly lost forever. But could future detectors, perhaps quantum ones, ever recover this information? Let us begin with what we know about black holes. When a star collapses under its own gravity, it can form a region of space so dense that not even light can escape. This is a black hole. According to general relativity, anything that crosses the event horizon is gone forever. But according to quantum mechanics, this poses a problem. Why? Because in quantum theory, information can never be destroyed. If you burn a book, its content is scrambled but not lost. You could, in theory, reconstruct the original state from the ashes and smoke. But when something falls into a black hole, the information about its quantum state appears to vanish, violating this fundamental law. This contradiction is known as the black hole information paradox. Stephen Hawking complicated the issue in the 1970s by showing that black holes radiate energy over time, what we now call Hawking radiation. This radiation seems to be purely thermal, containing no information about the particles that fell in. Eventually, a black hole evaporates, leaving behind nothing. So, where did the information go? Could it be hidden in the Hawking radiation itself? This has led to the idea of information reentry. Perhaps the lost information is somehow encoded in the correlations between Hawking radiation particles, or even in subtle fluctuations in the radiation over time. Theoretical models like the Page curve suggest that information may begin to leak out after the black hole has radiated away half of its mass. In other words, the radiation might not be truly random, but highly entangled with the past. Now comes the exciting question: could we ever detect this information with future technology? Quantum physicists propose that if we had a detector sensitive enough to measure the entanglement structure of outgoing Hawking radiation, a kind of quantum interferometer that could track phase correlations, we might one day see evidence that information is reemerging. This would require not just capturing individual photons, but measuring how they're entangled with others across vast time intervals. Some bold proposals even suggest that quantum gravity or holographic duality, like the ETS/CFT correspondence, allows information to be preserved, not in 3D space, but on the 2D boundary of space-time. This leads to ideas like black hole complementarity and firewalls, which attempt to reconcile information retention with the no-escape horizon. But could there be a physical device, an actual information reader? The black hole information paradox arises from the apparent contradiction between quantum mechanics and general relativity. According to quantum theory, information is never lost. It may change form but remains conserved. However, black hole evaporation via Hawking radiation appears to destroy information, since this radiation is purely thermal and contains no imprint of what fell in. If true, this would violate unitarity, a core principle of quantum theory. The paradox challenges our understanding of the fundamental laws of nature. If you throw a diary into a black hole, it seemingly disappears without a trace. It is like shredding a novel and watching even the shreds vanish into thin air. Can the story ever be recovered? Stephen Hawking's theoretical discovery in 1974 showed that black holes emit radiation due to quantum fluctuations near the event horizon. This Hawking radiation has a thermal blackbody spectrum, which means it appears random and contains no information about the initial state of the matter that fell in. As the black hole evaporates, it emits more radiation, eventually disappearing completely. If this process leaves no trace of the original matter, it leads to information loss. This conflicts with the idea that the quantum wave function must evolve in a reversible deterministic way. A black hole evaporating entirely would be like burning a book and never being able to reconstruct the text from the smoke. Hawking radiation is like white noise from a broken radio. It may once have carried a song, but all structure is gone. The AD/CFT correspondence from string theory offers a possible resolution by suggesting that black holes can be described by quantum field theories on a boundary of space. This duality implies that the information is not truly lost, it is encoded in subtle correlations within Hawking radiation or the space-time geometry itself. Furthermore, the island paradigm from quantum gravity proposes that certain regions inside the black hole are entangled with radiation outside, preserving unitarity. These new insights support the idea that information may not be lost but scrambled and recoverable in principle. The Page curve, which describes entropy over time, suggests that late Hawking radiation carries increasing information. It is like a burned diary whose ashes slowly rearrange themselves into legible text as time passes. In theory, if Hawking radiation carries information in its fine-grained correlations, ultrasensitive detectors could recover it. But these correlations are incredibly subtle. They exist not in the intensity or spectrum of radiation, but in quantum entanglement patterns. Detecting them would require a quantum computer capable of decoding massive entangled systems, possibly using error correction principles. Practical detection is currently beyond our capabilities, but theoretically it does not violate known physics. Progress in quantum computing and space-based interferometry may one day test these predictions. NASA's future LISA mission will probe gravitational waves, but quantum information detectors would need even greater sensitivity. Measuring this information is like trying to reconstruct a whispered conversation from echoes in a canyon, possible in theory, but requiring extreme precision. One controversial resolution is the firewall hypothesis, which suggests that infalling observers would be incinerated at the event horizon, breaking general relativity. Others propose soft hair, quantum fields that live on the horizon and can encode information subtly. These theories aim to retain both quantum and gravitational consistency. Each comes with philosophical and empirical challenges, but they broaden the conceptual landscape for recovering information. None are yet universally accepted, but all attempt to salvage unitarity without violating relativity. Hawking himself later supported soft hair as a possible mechanism for storing information on the horizon. Soft hair is like a cosmic barcode printed on the black hole's skin, hard to read but not erased. While we cannot access actual black holes, scientists create analog systems that mimic aspects of black hole behavior, such as sonic black holes in Bose-Einstein condensates or light trapping in optical fibers. These experiments have reproduced thermal spectra akin to Hawking radiation, offering testbeds for some theories. Although these analogs do not emit real quantum gravitational radiation, they offer insights into entanglement dynamics and event horizon behavior. Studying these systems could guide the design of future quantum information detectors. This bottom-up approach complements theoretical top-down models. A 2019 experiment using ultra-cold atoms simulated a Hawking-like horizon and observed information-preserving behaviors. These analogs are like flight simulators for quantum gravity, imitations that teach us about the real thing. Recent theories suggest that entanglement itself may be the glue holding space-time together, a concept known as ER equals EPR, Einstein-Rosen bridges equals entangled particles. If true, the structure inside a black hole may not be a physical location, but a pattern of entangled quantum states. Information could then reemerge from this entangled geometry as black holes radiate. This reframes black holes as quantum computers that scramble but do not erase information. Recovering it would require decoding the space-time entanglement structure. Quantum teleportation experiments have demonstrated that entangled particles can transmit states without transmitting matter. The black hole interior is not a vault but a quantum code, hidden, encrypted, and possibly decodable. Even if information is recoverable in principle, practical constraints may render it inaccessible. The energy required to capture all Hawking radiation, store it coherently, and decode it could exceed cosmic limits. Quantum noise, decoherence, and background radiation would swamp the signal unless filtered with precision beyond current technology. Moreover, the timescales involved are enormous. Black holes evaporate over trillions of years. Thus, while information may never be truly destroyed, it may be practically unrecoverable. A solar mass black hole would take tilde 1067 years to fully evaporate, far beyond any human experiment. Trying to extract this information is like trying to unbake a cake by watching it cool over eternity. The black hole information paradox is no longer about whether information is lost, but whether we can prove and access its survival. Quantum gravity, holography, and entanglement all support the idea that information is preserved in black hole evaporation. Future detectors, possibly built on quantum computing, entangled photon arrays, or space based interferometers, might decode this information. If successful, it would confirm deep connections between gravity and quantum mechanics, possibly offering a glimpse into a theory of everything. Until then, black holes remain cosmic puzzles storing secrets in quantum riddles. The quest to read Hawking radiation correlations is ongoing in black hole thermodynamics and quantum information labs worldwide. The universe may be whispering secrets through black holes. We just haven't built ears sensitive enough to hear them yet.